What we are going to work with today is a continuation of what we worked with yesterday. So before we dive in with what we're actually going to look at today, I want to show you how what we're going to do today is what we're connected to what we did yesterday. So yesterday, we were working with diagrams that look kind of like this. So we had a couple of parallel lines. So we'll put our parallel marks, so those are parallel lines. And we had a transversal going across those parallel lines like this. So we also had a second transversal going across those lines. And what's going to change today has to do with that second transversal. So I'm actually going to put it kind of down here. I'm going to draw a copy of it intentionally off the diagram because I want to be able to move it around. So I'm going to do something here. So now I have one that's movable. So yesterday, our diagrams looked like that. So you could see the top triangle, kind of upside down triangle, and the right side up triangle between the parallel lines, and those were our similar triangles. So if you go like that, you have like a smaller one and a bigger one, but they're similar. So what I'm going to do is I'm going to take this transversal line from yesterday and I am going to slide it over. So you can see I'm sliding it over. And if I slide it over far enough, so yesterday I had both triangles between the parallel lines. One was upside down, one was right side up. But if I slide this far enough, that second triangle is no longer inside the parallel lines. It is now up here. And it is similar to another triangle that it's actually inside of. So you can see this kind of great big triangle down here. So if we take the line, one of our lines from yesterday, and we just slide it over like I showed you, you could see when I moved the line over a minute ago that if you slide the line over far enough, it's going to change where your similar triangles are. So it's still a connected diagram because it's still two transversals crossing over the parallel lines. What we changed was just where are the transversals. So if the transversals are far enough apart, then it's going to create a situation like this where you've got this little triangle inside a bigger similar triangle. So what we're going to look at today are some diagrams like this, because this is kind of the other variation of what can happen when you have a setup with two transversals crossing over parallel lines, making similar triangles. Because the triangles are in different positions, we have to deal with them slightly differently. So that's why we're taking a day today to talk about this setup, which is a variation of yesterday's setup. So now that you've seen kind of how does yesterday connect today, all we did was we just slid that transversal over, but it changed where the triangles are. We're going to talk a little bit about this diagram today. So hopping into your notes for the day, we're going to do a couple of things. First of all, we've got a picture of this diagram with all of our angles and things labeled. And what we're going to do as part of our notes is we are going to mark up this diagram and label some things on this diagram so that you know where the matching, so corresponding sides are and where the matching angles are and why we could say that these triangles are similar. What's our proof? So we're going to kind of thoroughly talk through and write down some things about the diagram. And then our second problem is kind of like yesterday, we're going to do some practice calculating with the diagram. So similar to yesterday, but with our new variation of the diagram. So first things first, we said that we have two similar triangles in this diagram. So I'm going to kind of go through, I'm going to highlight those again. So we've got this yellow triangle here, and it is similar to this red triangle out here. So it's actually inside that triangle. So those are our two similar triangles. So we can go through and we can make our similarity statement about those triangles. So triangle DCE, the little triangle, is similar to, remember that's our symbol for similar. It's kind of like congruent, but it's missing a part because they're not the same size. Triangle. Remember, we want to name things in the same order. So these triangles are both facing the same direction. It's not like yesterday's diagram where you had one of them spun around upside down. These really are facing the same way. So bottom left corner is going to match bottom left corner. So the bottom left corner of the red triangle, since that's what we started with on the yellow triangle, would be A. and then we went up to the top. So A, C, B, if we want to put it in matching order, which we should. So those are our triangles. They are similar. We can use some of what we know about our angle relationships of parallel lines to explain why they're similar. So if you look at angle 3 and angle 1, that's the bottom left angle of both triangles. So that is formed, I'm going to draw it kind of small here. So I'm going to ignore the transversal as those angles aren't on. Angle 1 and angle 3 are both kind of on that line. So angle 3 is right there. Oops, sorry. I put it in the wrong spot. Angle 3 is up here. And angle 1 is right there. So if you kind of ignore the right side of the triangle, the other transversal, and just focus in on that, those are corresponding angles. And we know that corresponding angles are congruent. So angle 1 is are congruent to angle 3 because they're corresponding angles. So we're kind of using the definition of corresponding angles to argue that, because the definition of corresponding angles is that they're congruent when they're crossing parallel lines. So I can add congruent marks there. I can prove they're congruent because they're corresponding angles. Now if I look on the other side of the triangle, angle 4 and angle 2, so here's my parallel lines, and if I look at the line that's going this way, angle 4 is right there, and angle 2 is right there. That's another pair of corresponding angles. So angle 4 is also going to be congruent to angle 2 because they are also corresponding angles. So I have two different pairs of corresponding angles in this diagram. So I can label 4 and 2. I'll put 2 arc marks since that's a different pair of angles. So those are congruent. And then the top angle up here, angle C, that is the top of both triangles. It's the top of the yellow triangle and it's the top of the red triangle. So they are literally sharing that exact same angle. Since they're sharing the exact same angle, of course that angle is going to be the same for both triangles because it's literally the same angle. So that by matching up our corresponding angles and by looking at the angle that they are literally sharing at the top of the triangle, we can prove that all of the corresponding angles are congruent. And we know from yesterday when we talked about similar triangles that when all of the angles are congruent, two shapes will be similar. So that proves or kind of backs up our statement that we made about the triangles being similar. Now there's one other thing, and so what I'm writing down, you should be writing down in your notes. So you should have this little kind of argument off to the side all mapped out here. There's one other thing I want to do that's very important, and it has to do with matching up the sides of the triangles. So when you draw these triangles, so if you're a good trick with these, because one triangle is inside the other triangle. So my advice when you have one triangle in another triangle when you're calculating is to actually redraw the triangles separately. And I want to show you why. So this guy, here's our little triangle, DCE, right? Our big triangle looks like this. So we've got that kind of line running through the middle where the little triangle's inside it, right? What I want to point out, and we're going to reinforce this in just a minute with our practice problem, so ACB, if we match up matching sides of the triangle, so the bottoms of the triangles are corresponding sides, so that's easy because they're facing the same direction. Where this gets a little tricky is with the left and the right. So if you look up here, or if you pay close attention, here's the left side. So where people get confused is the left side of the big triangle has two parts. I'm going to kind of put a little break in here so you can see. It's got this bottom part, but it's also got the top part that's the little triangle side. So you have to put both of those parts together to get that whole side. So a really common mistake that people make is they forget to label, or they forget to make sure that they're looking at the entire side of the big triangle because the little triangle's in there kind of breaking it up. So it's really easy to get visually tricked. So that's something we're going to talk about more in just a second, but I want to point that out. When you have a triangle inside another triangle, you have to make sure that the bigger triangle, you're not accidentally chopping off parts of side lengths. So on that note, and also expanding on that so you can see more about what I mean with that, we're going to look at an example problem. So this problem has A, B, C, D, and E hiding in it. So we're going to work through them in order. So we're going to start with A. So A is right there. Now we know that, so the first thing you should look at, because we know that similar triangles have congruent angles. In other words, the angle measures are the same. So the very first thing you should try to do when you've got a missing angle measure is look at the other triangle. And if you see if you know that angle, and if you do, then you've got the answer because they're the same. So in this case, we don't, because the matching angle for A is C. Well, we don't know either of them. So we have to approach this slightly differently. The second thing you should always keep an eye out for and try and remember is that we know the angles in a triangle add up to 180 degrees. So in this case, we can use that to figure out angle A, because if you look at the little triangle, we know both of the other angles. We know this is 39 and this is 76. So if we take those, we know 39 plus 76 plus whatever A is. So 39 plus 76 plus A equals 180. And you should be writing down these calculations in your notes too, to make your notes helpful to you. That way, if you're looking back at a similar problem later, you remember how we got those answers. And that's what makes your notes useful. If all you have is an answer on a page, that's not going to help you remember how to get that answer. So you should be writing down the calculations that I'm writing down to make your notes as useful as possible. So how we're going to get A is by playing off the fact that we know the angles in the little triangle add up to 180. So we would work backwards and we would subtract the angles we know out from 180. So basically we'd solve that little equation we just wrote down. And if you do that, then you should get 65 degrees for A. So we know that A is a 65-degree angle. And I'm going to take that, and I'm even going to just kind of off to the side here, I'm going to write that down so that you remember that, because that's going to come in handy in just a second. So our next angle, angle B. So we said that the first thing you should always do is check and see if you know the matching angle. So bottom right angle of the big triangle matches bottom right angle of the little triangle. And oh, look, we know what the bottom right angle is. So if the little triangle's bottom right angle is 76, then the matching angle of the big triangle also has to be 76. So that one was just matching angles. That was pretty easy. We didn't have to calculate anything. So now, angle C. So angle C is down here. And this matches with angle A, but we just figured out what angle A is. So now that we've got angle A, we can just use matching angles again for angle C. So if the bottom left of the little triangle is 65, then the bottom left of the big triangle is its matching congruent angle. It's also going to be 65. So both of these we just figured out by looking at corresponding angles. So if you want to put a note of that so that you remember later how we figured that out. So we use corresponding angles to get those. Now, D and E. So D is down here. It is not an angle. It is a side length. So if you remember what I was saying before about my advice when you have one triangle inside another triangle to draw the triangles out separately, we are actually going to do that before we try and calculate D and E, which is also a side length. So those are both side lengths. So, and you're going to see why now that we've got numbers labeled in there, I suggest that you draw the triangle separately. So I'm going to take, and we're just going to focus on the side lengths because we know all the angles. D and E are missing side lengths. So this triangle, this is our little triangle. It is 24, 21, and 14. So we know all of the measurements of the little triangle. Now we've got our big triangle. So our big triangle, the bottom is D. That's what we're missing. So kind of looks like this. So we've got 24 and E, and then we've got 21 and 42. So the thing we have to be careful of is the sides of the triangle. So the little triangle side, in order to get the matching side for that, this is the right side of the little triangle. the right side of the big triangle is not just this, it's the whole thing. So in order to get the total length of that side, because the side is being given to you in two parts, you're going to have to add those numbers together to get the total length of the side. So a lot of people get tricked by that and they'll just use the 42. Well, 42 is not the entire right side of the triangle. It's only part of the right side. So you have to make sure that you're getting the length of the entire side of the triangle. So don't get tricked by that. That's a common mistake that people make when they have shapes inside other shapes. So the entire side length of the big triangle is not 42 and it's not 21. It is actually 63. So 21 matches with 63. So that's why I suggest drawing the diagram separately, because it's harder to miss pieces of your triangle when the triangles are separated out. So it's something to just kind of organize your thinking a little bit so that you don't get tricked by things like that. So back to D. So since D is a side length, yesterday we said to find side lengths, we know that similar figures have, the corresponding sides have equivalent ratios. So we can find a side that we're not missing any information for. So in this case, our two triangles, we know the right side of both triangles. So I can start by making a ratio of those two right sides. So 21, so little triangle compared to big triangle, 21 matches with 63. So I got my little triangle on top and my big triangle on bottom. So I want to make sure I keep it that way. So now I can make a ratio with what I am trying to figure out. So D is the bottom side, so it's going to match with the bottom side of the little triangle. So since the ratios are the same, 21 over 63 should be the same as 14 over whatever D is. So that makes a proportion with the sides. Now I can go through and solve that proportion. So cross multiply, I know, is the favorite way for most of you guys. So if I do 63 times 14, I get 882. We're tracking through this quickly because you guys should know how to solve a proportion. Divide by 21, and we get 42. So that means D is 42. So angles, if you're missing angles, look for matching angles. Look for angles in a triangle that you can add up to 180. If you're missing sides in similar figures, then you should be using ratios and proportions. So angles, match them up, add them up to 180. Side lengths, make a proportion. So it's kind of different calculations and different ways of handling depending upon what you're missing, an angle versus a side length. So we are missing one other side length here, and this last one, I'm going to erase all this down here. This was from the intro to the video where I was showing you how the transversal moved, but I need the space. Okay, so E is going to be a little bit trickier because E is actually part of a side length. So I want to walk you through how that works. So E is part of the big side of the triangle. So before we can find E, we actually need to find the entire big side of the triangle. So the way that's going to work is by matching up the left side. So this first step is not going to actually calculate E. It's going to calculate that entire blue length. So from here all the way to here. But if we know that whole thing, then we'll be able to figure out E from there. And we'll get to that in just a minute. So if you're calculating something that's part of a side length, then you have to start by finding the whole side length first and then go from there. So we're going to start by finding the whole side lengths first. So we're going to reuse those yellow ratio again. So little triangle to big triangle, 21 to 63. And then if we do the blue sides, the little triangle is 24 and the big triangle is 24 plus E. Because remember, we have to add the sides together to get the whole thing. So this whole thing is going to be both parts together. It's not just going to be E. E is not the whole side length. So we have to make sure we're comparing it to the entire side length. So 24 over 24 plus E. So this is where your solving equation skills are going to come into play, because when you go to cross multiply this, so this way is easy. 63 times 24. Well, that's just regular old multiplication because we know both of the numbers there. So that's going to give us 1,512. When I multiply this way, I have to be careful though, and I'm actually going to kind of write this out in 2 steps. So this 24 plus e, that whole thing has to get multiplied by 21. So what you're going to actually end up doing is a little bit of distributive property there, because the 24 has to be multiplied by the 21 and the e has to be multiplied by the 21. So when you've got a kind of 2-part thing where you're missing part of a side like this, it's going to introduce a little bit more complexity into your proportion, but a little bit of distributive property solves the problem. So now we've got our equation. We just have to solve this out. So 21 times 24, if we do our distributive property, is 504. And then 21 times e is 21e. So that makes a 2-step equation. So now we can solve our 2-step equation. So 504 minus 1,512 gives us 1,008. That cancels. We still have the 21e, and then divide by 21. And we get e equal to 48. So there's your answer. So that's what I was saying about how you have to be careful, because right here, that's not just going to be e if e is only part of your side length. So these diagrams, I think, are a little bit trickier than the ones we were working with yesterday, which is why we saved them for day 2. And the thing that's tricky is that you have to keep track, because you have one triangle inside another triangle. And the big triangle, you have to keep track of those partial side lengths, because when you're calculating, we calculate with whole side lengths, not partial side lengths. So sometimes you might have to add some numbers together. So like on the yellow side, we had to add 21 and 42 to get the whole side of 63. Or we had to add 24 and e in our proportion to get the entire blue side length that goes with the 24 on the small triangle. So sometimes you have to do some adding or putting together parts when you have a diagram with a shape inside another similar shape like this. So what you're going to do today is you're going to try some practice similar to yesterday's practice. So you're going to have a diagram with some questions to answer about it, and then you're going to try a problem really similar to this problem that we did together to see if you're able to work through these calculations on your own, but with our new variation of the diagram from today. And just another reminder before we go and do that, make sure that all of these calculations that we have written down for how we got the different side lengths are also in your notes. That way, if you look back at your notes later and you're trying to remember how to do a problem, you have the steps to look at. If you're just staring at the answer, that's not going to help you remember how you got your answer. So I am going to be checking to make sure that you wrote down all of your calculations in order for you to get full credit for your notes. So on that note, when you are ready, you can go ahead and try today's assignment.